Okay, guys, today we are looking at 14.3, which is multiplying radicals. Okay, so when we look at multiplying radicals, we want to start with the product property of radicals. Now, we've looked at this before, and really all it says is that if we take the square root of a times the square root of b, it's the same thing as the square root of ab. Okay, so we'll just multiply these numbers underneath the radical or in our radicand, okay, and they will combine under the same square root. Okay, we've seen this before. This should be pretty familiar with us, or familiar to us, excuse me. Okay, for the commutative property of multiplication, I know we've talked about it quite a bit in my classes. In the commutative property, all it really says is if I have a times b, that's the same thing as b times a. So I like to use examples of this, like 2 times 3. Well, we all know 2 times 3 is 6. Well, it's the same thing as 3 times 2, which is also 6. Okay, and that's the same for whether you have two numbers on each side or 3 or 4. Basically, what we're saying is if we are multiplying two numbers or three numbers or more, it doesn't really matter how many numbers we have. As long as they're all multiplication, we can rearrange the order and get the same product. That's what it means to be commutative. Okay, so addition is also commutative. As long as they're all addition or all multiplication, okay, in this case, we're looking at strictly multiplying. It doesn't matter what order we have them in. So for instance, in this 3 part 1, we have a times b times c. That's the same as c times a times b and b times a times c. Okay, so there's all those different possibilities. As long as it's all multiplication, it does not matter what order we do it in. We're going to get the same product. Okay, so these are two kind of important properties to remember for this section. So we're going to start by multiplying the square root of 2 times the square root of 2. Well, of course, using our product property of radicals, we know that's just the square root of 2 times 2. Well, 2 times 2 is 4. And the square root of 4, we know 4 is a perfect square. Square root of 4 is 2. Okay? So looking at number 2, I have square root of 11 times square root of 11. Remember, we can represent multiplication a lot of different ways, guys. The asterisk, okay, that means multiplication. Parentheses means multiplication. The little dot means multiplication, okay? Square root of 11 times the square root of 11 would give me the square root of 11 times 11, which is the square root of 121, which of course is 11. So if we notice, when we multiply two things together, it's like the square root of 2 times the square root of 2, what do we end up with? Just 2. Or the square root of 11 times the square root of 11, it's just 11, right? We know that this is going to end up being 11 times 11, which is going to give me a perfect square. Anything times itself is going to give me a perfect square. So if I have the square root of something times the square root of that exact same something, my answer is just going to end up being whatever number is underneath the radical sign. Okay, that's an important rule to remember. Number 3, I have the square root of 3 times the square root of 12. It's going to give me the square root of 3 times 12. And 3 times 12 is 36. And 36, of course, is a perfect square. And the square root of that perfect square is 6. Okay, so we're going to start off some 3 easy ones there. Again, it's important that we be able to recognize what our perfect squares are. And all 3 of these ended up being perfect squares, so we end up with nice numbers there. This rule right here, again, that property is important to remember. Square root of 2 times square root of 2 is just going to end up giving me 2. Okay, so let's look at number 4. For number 4, I have 2 root 3 times 4 root 3. Here, I'm going to multiply the outside stuff together. Okay, 2 times 4, and then I'm going to multiply the radicals together. Root 3 times root 3. 2 times 4 is 8, and then root 3 times root 3 is root 9. Of course, we know 9 is a perfect square, and of course, looking at this rule here, we should remember that little rule I was talking about in the last slide. Root 3 times root 3 is the square root of 9. Well, the square root of 9, we all know, hopefully, is 3. So I have 8 times 3, which is 24. Okay, so this process is really, we're going to take the radicals and multiply them by each other, my coefficients and multiply them by each other. I'm just going to simplify from there. We know 9 is a perfect square. Of course, 8 written right next to this radical means I'm going to multiply, so 8 times 3 is 24. Okay, for the next one, I have 3 root 10 times 5 root 20. I'm going to take my coefficients times each other again, 3 times 5. I'm going to take root 10 times root 20. I'm going to get 15 root 200. Okay, 200 is not a perfect square, so we need to find the highest perfect square factor that goes into 200. This one shouldn't be too hard to think about, but I'm going to give you a couple seconds to think about it. Okay. Hopefully, we know that the highest perfect square that goes into 200 is 100. I'm going to take 15 times the square root of 100 times the square root of 2. So here's that little branching method that we talk about when we're taking out our perfect square factors. Okay. Square root of 100 is 10. So I would have 15 times 10 root 2. Well, 15 times 10 is going to give me 150. So I would have 150 times the square root of 2. I can't simplify the square root of 2 any more than it already is. Okay. So this right here is my final answer, 150 times the square root of 2. Okay. For number 6, I have 5 root 10 times 5 root 10, or times root 10, excuse me. Again, here's another way we represent multiplication. We haven't seen this one a lot this year because we use variables a lot, and sometimes those variables x can look like this, so we try to avoid this, but that doesn't mean we can't see it, okay? So 5 root 10 times root 10 is going to give me 5 root 100, because 10 times 10 is 100. That property right there is our product property of radicals, right? Okay, and of course we know the square root of 100, it's a perfect square, is 10, so 5 times 10 is 50. Okay, so this multiplication stuff, I think once we kind of get the hang of it and do some example problems, it won't be too bad on any of us. But we just, again, need to remember how to simplify radicals and our product properties, and we'll be okay. Now, we're going to look at multiplying using the distributive property, okay? Distributive property is a little different, but of course, hopefully we remember the distributive property. If I have a parentheses b plus c, it is equal to ab plus ac. So again, I'm going to distribute this a to everything inside parentheses. Remember what it means to distribute something. A times b is ab, a times c is ac. Okay? So remember, we're distributing everything outside the parentheses that's right next to it to the stuff inside. So if I look at the first one, I have root 3 parentheses 7 plus root 3. I'm going to distribute root 3 to 7. And I'm going to distribute root 3 to root 3. So root 3 times 7 is 7 root 3. That might look a little funky to us, but remember, if it's a coefficient or a regular number, I usually write it out front of the radical. So I have 7 root 3 plus root 3 times root 3 is root 9. Okay, and let's simplify this if we can. 7 root 3 plus the square root of 9. Well, 9 is a perfect square. And we, of course, know, hopefully, that the square root of 9 is 3. So I'd have 7 root 3 plus 3. And right there, we can't simplify this anymore, okay? So if you have 7 root 3 plus 3, okay, this, again, I talked about addition being commutative as well. These two last lines right here are pretty much the exact same thing. Sometimes it's common practice to write the stuff without a radical first, but these are the exact same thing because addition is commutative. It doesn't matter what order we have it in, okay? So these two things, either one, I would take as an answer, okay? For number 2, I have 2 root 7 parentheses 3 root 2 minus root 5. Okay, I'm going to distribute 2 root 7 to everything inside the parentheses. Well, 2 root 7 times 3 root 2 is going to give me 6. 2 times 3 is 6. And root 7 times root 2 is root 14. Okay, that's my first one. That's where all this stuff's coming from. 2 root 7 times negative root 5 would give me negative 2, because remember, there's an imaginary 1 out here. 2 times negative 1 is negative 2. And root 7 times root 5 is root 35. So what we're going to try and do here is we're going to try and see if either of these are perfect squares or if there's perfect squares I can take out. Okay, of course, sorry about that, guys. There are not. There's no perfect square that goes into 14. There's no perfect square that goes into 35. So this right here would be as simplified as I can get that answer. That's it right there. 6 root 14 minus 2 root 35. Okay, not too bad. Sometimes that will happen where we get radicands that actually can't be simplified. Don't be shocked when that happens, because it is possible. Okay, looking at number 3, I have negative root 5 parentheses 2 root 15 minus 3 root 10. Again, I'm going to distribute to everything inside the parentheses. Well, negative 1 times 2 is negative 2. Root 5 times root 15 is the square root of 75. Negative 1 times negative 3 is a positive 3. That's where that's coming from. Okay, and the square root of 5 times the square root of 10 is the square root of 50. Okay, now I need to double check these and see if there's a perfect square that goes into either of them. Of course, there is. 25 is a perfect square that goes into both of them. Think of money, think of quarters, right? So I would have negative 2 root 25 root 3 plus 3 root 25 root 2. Hopefully we all know by now 25 is a perfect square, so we can actually take the square root of both 25s that are there. And the square root of 25 is 5. So I'd get negative 2 times 5 root 3 plus 3 times 5 root 2. So from this step here to that step that we just had come up on the slide, we're just taking the square root of 25. Okay? So negative 2 times 5 root 3 would give me negative 10 root 3. And 3 times 5 root 2 would give me 15 root 2. And of course, we need to be able to check at this step here. Once it's all simplified, guys, we should be able to check and say, okay, can I add or subtract, or in other words, combine my like terms? Well, these aren't like terms because one's the square root of 3 and one's the square root of 2. So this right here would be my most simplified answer, negative 10 root 3 plus 15 root 2. Okay? Looking at number 4. Number 4 is a little different, right? Up until this point, we've just had one term outside the parentheses. Well, here we have two binomials. We have two two sets of parentheses with two different terms. Okay, so what we're going to do is we're going to distribute using our FOIL method. Hopefully you remember that. So first, negative 8 times 8. Outside, negative 8 times root 14, my outside terms. Inside, okay. Well, I guess we're going to simplify those first. That's okay. So negative 8 times 8 is negative 64. Negative 8 times root 14 is negative 8 root 14. Okay. Now I'm going to do my inside terms. Hopefully remember FOIL, the acronym. First, outside, inside, last. Okay. Root 14 times 8 is 8 root 14. And then root 14 times root 14 is the square root of 196. 14 times 14 is 196. Okay. We notice something here. Do I have like terms? Right? I do have like terms right here, don't I? Negative 8 root 14 plus 8 root 14. They both have the square root of 14 attached to them. But negative 8 plus 8, that would give me 0. They would cancel out. So we notice that these here, these are something special that we actually have talked about briefly this year. Okay. They're called conjugates. Hopefully you remember that. Okay. They're the exact same thing. The only thing that's different between them is a sign, right? This is a negative 8, and that's a positive 8. Okay, that's the only difference. And we know that those are going to cancel out, so I'd get negative 64 plus 14, the square root of 196. It's a perfect square. It's 14. I can do negative 64 plus 14. That is negative 50. Okay, so sometimes there's a few more steps that we need to remember and some tips that we need to remember when it comes to actually doing these problems, guys. But as long as we remember most of these and get these written down step by step, excuse me, I think we'll be okay. So moving on to what would be number 5. I know it's number 2, but it's actually number 5. I have 3 plus the square root of 17 times 3 minus the square root of 17. Again, we notice these are conjugates, right? The only difference is this sign here. I have 3 plus root 17 and 3 minus root 17. So I want us to notice what's going to happen. So I'm going to FOIL again. I'm going to get 9 minus 3 root 17 for my first and outside terms. I'm going to take my inside terms. Root 17 times 3 is 3 root 17, and root 17 times negative root 17 would be, oh, sorry guys, this should be a negative root 289 here, because root 17 times negative root 17 would be negative 289. Okay, so change this plus sign to a minus. Okay, so again, we notice my middle terms are going to cancel out here. So I would get 9 minus 17, not plus. Again, that should be a minus sign. So instead of the answer being 26 here, guys, it should say 9 minus 17, which is, what do we think? Negative 8. Okay, negative 8. So we need to remember that these are conjugates and that usually our terms, we're going to have some terms cancel out when we work with conjugates, okay? Looking at number 3, sorry about that mess up there, guys. That's my fault, okay? Looking at number 3, I have 5 minus root 2 and 5 plus root 2. Again, they're conjugates. I'm going to FOIL. I'm going to get 25 plus 5 root 2. And, oh, these arrows should be moved over here. And negative 5 root 2 plus root 4. Again, this should be minus root 4, not plus root 4. Messed that up twice. Okay, so these are going to cancel out. I would get 25 minus 2, which is actually going to be 23. Sorry about those mess ups on these last two, guys, but make sure you're taking note of that. Okay, a positive times a negative is a negative, not a positive. Okay, you guys can all give Mr. McLaughlin some grief over that. Okay, even math teachers mess up sometimes, right? Okay, so that is it for today, guys. Let us know if you have any questions. And remember just our regular product rules and property rules, okay?